I don't know.
Well, yeah, Carlos,
Yeah.
okay, I could go and get it.
No, it's okay.
Is it okay?
Yeah.
Okay.
So, hi everyone, and welcome to our last seminar of the season. So today we have the pleasure to welcome Kara Nelson from the University of Massachusetts in Boston. And the topic of the talk will be towards study of photon dynamics in non-separable spacetimes. As usual, there's time for questions at the end, but also feel free to ask during the talk. And Kara, thanks a lot for being here, and you have the floor.
Okay, well, thank you guys for having me. I didn't realize it was the last seminar of the season, so I hope we end well. Yeah, so just a little bit about me. I am from Boston, lived here in LA. I was just in Lisbon for a gravitational collapse conference, and I'm excited to change topics because it was 4 days of kind of the same stuff. So yeah, I just finished my thesis, my master's thesis, and I worked with Prashant. He was at the Black Hole Initiative at Harvard, so he's been kind of introducing me to EHT and ray tracing and whatnot. So today I'm going to be talking about what we kind of developed for my master's thesis, which was a ray tracer that is applicable to more general metrics without separability. And yeah, I'll walk through kind of the motivation for this, as well as how we developed it, some of the validation that we used, and then a preliminary kind of next step that we're working on right now. So as we know, next generation EHT is going to be happening, and we're going to be getting some much better images of black holes, including the black hole shadow, a little bit more structure and resolution there, as well as the photon ring, which is composed of higher order images or photons that circle the black hole multiple times. So this is kind of our next generation of imaging. We'll be having more telescopes on the Earth, and then we're also going to be having a telescope in space. So we'll be having a more diverse amount of baselines and then longer baselines, and this will increase our angular resolution. So our images are going to get a lot better in the next coming years, and we need a way to analyze these, decide kind of what we're looking at. And yeah, we also need to understand kind of more diverse imaging. So not necessarily a Kerr or a Schwarzschild, which we know really isn't very realistic. And so this is kind of one of our motivations, is to have these different types of models, different imaging, kind of imaging predictions. And yeah, so this is kind of one of the motivations for the coming project or the coming years. And we will be focusing very intensely on the photon or the black hole shadow and the photon ring. So as we know, models are incredibly important. We use models to kind of tell us what we're looking at in this image. So here we have, a model of M87, I want to say, yeah, M87, and kind of showing our model versus the actual image that we got. So having these really not only robust, but a variety of different types of models are really important to understand the image that we're looking at. And so this is kind of our stage right now of imaging, and we're hoping in the next couple of years to also be able to get a little bit more resolution and this defined photon ring. And these are really important because they encode a lot of information about the underlying space-time geometry of the black hole. So we'll get into this later, but these photons are spending a very long time around the photon region. So studying these areas tell us a lot about kind of what's going on close to the events. Okay, So obviously we talk a lot about Kerr. There's a lot of reasons why we talk about Kerr so much. It's very well understood. People have studied it significantly. It is a separable metric, so it's very easy to code and come up with these analytical values, either by pen and paper or numerically. And so we know a lot about this, this space-time. And yeah, one of the reasons why we know so much about it is because it's a nice equation. It's separable. And what I mean by that is you can write the potentials in terms of R and in terms of theta, and you don't have any of these mixed terms. So it's very easy to code. It's very easy to find analytical quantities, and they've been calculated in very quick ways and efficient ways. But we want to kind of extend this framework into more general space-time. So there's really no guarantee that an image of a black hole is going to occur. It's almost too nice of an equation. So we want to be able to kind of take this separability, this nice quality, out of our framework and not even worry about it, and be able to kind of look at these more general spacetimes in order to kind of explore different metrics as well as be able to calculate some quantities in order to help us kind of motivate these images that we're going to be getting. So we do not have a Carter constant in our framework, and we're not assuming any separability. You can have separability, but one of the goals of this is not to. So yeah, you need some direct numerical methods. You need kind of a new way of doing things where you can't rely on these nice qualities. So as you guys all know this, why do we care about going beyond Kerr? We know that Kerr is, really nice to study and a little bit more complicated than a Schwarzschild, but there's really no guarantee that an image is going to look like a Kerr or not. So when we kind of extend this to more general spacetimes or just different spacetimes, more complicated ones, we can learn a lot about kind of the image that we're looking at. So, testing these more general spacetimes, kind of get an idea of the black hole that we're looking at, the spacetime that it lives in, and this is able to kind of test whether we're correct with general relativity. And we can also test alternative theories. And then also there's just, different spacetimes are going to produce different observables, right? So we need to be able to kind of have a way to quantify these observables and kind of know what we're going to be expecting. And then things like exotic compact objects might have, a Kerr-like shadow, but not be a Kerr black hole. So we need kind of different ways to distinguish these models and these images. And one of those ways is kind of what we're doing. And yeah, just extending to more general spacetimes. Okay, so goals of this work, we set out to develop and validate a very general ray tracer and be able to calculate some quantities and some kind of more observable aspects. So in our framework, we use a Hamiltonian evolution. It is does not depend on separability. It is metric independent. So one of the goals was to keep the framework completely the same. Really, the only thing you have to change is the metric itself. So that's really nice. You don't have to do a lot of these general ray tracers. You have to kind of hard code the derivatives and hard code analytic values. But for this one, we really just changed the metric that we're curious about. And this works for stationary axisymmetric spacetimes. And so some of the outputs that we were able to do is critical curves, so very important for the shape of the shadow, the structure of the shadow, as well as the near critical trajectories, which I said are really important because they spend a lot of time in the photon region. So studying these specific trajectories, we can learn a lot about the underlying spacetime. We also took a look at critical exponents, critical quantities. So instead of kind of a observational, or I guess qualitative view of the observables, we can get a quantitative calculation and description of the spacetime. So those are really nice. And I'll get into those a little bit more in detail, but we calculate the Lyapunov time as well as the delay time in the phase shift. So those are also very important for describing the space-time that we're living in, as well as they are super related to the photon ring, which we should be able to get in the future. Any questions so far? Yes.
Yes. So in this assumed framework, is space-time assumed to be circularity? Is that an assumption? Or so you have
no, really the only assumptions that we made is stationary, static, and stationary and axisymmetric. Those are our two assumptions.
And you don't assume either Z to symmetry between the north and south hemisphere?
No, we haven't assumed that, but that's the ones that we've looked at so far are equatorial symmetric. Okay, so next we're going to be talking about a little bit about the methodology. I'll try to be relatively quick with this. But like I said, we are doing a Hamiltonian evolution. We're doing a very classic ray tracing approach. Not sure if you guys are familiar, but the basic concept is that you start from very far away from the black hole and you integrate it backwards in time. So you get closer and closer to the black hole and kind of classify what happens, whether it plunges into the black hole, whether it escapes to infinity, or whether it is going to circle around multiple times or infinity. Yeah, so we took our observer position to be 40 M, so it has to be very far away from the black hole. We also have tested this with much larger ones. It just takes a very long time to run. So yeah, and then we started at 90 degrees based on, edge on observer and things like that. We also were able to kind of hard code the initial momentum vector. So some of these important quantities are our impact parameter, which is P5. This is going to decide what I guess the classification of the trajectory. So if you're far away from the black hole, you're not going to fall in, things like that. So this is very important. We've been varying this, as well as P theta, which is our initial polar momentum. So this is also going to have an effect on what the ultimate classification is of the trajectory. And then we use the null constraint to solve for our radial momentum. And the way we evolve it is using the Hamiltonian. And so we're able to actually numerically solve for these derivatives, and we kind of take it a step at a time. And the nice thing about this is that we're able to track all of our coordinates as we're going through the integration process. So, if you're curious about how the radial momentum is changing or something like that, you can track that. And we actually have some nice plots of kind of the time evolution of some of these coordinates. Yeah, so we use Runge-Kutta fourth order integration, which is nice because it's relatively simple to understand, and then it also is very robust and computationally efficient. We also use adaptive step sizing, which is nice. For the Hamiltonian, we use the Hamiltonian as kind of a tracking of these, of nice spots. Like turning points are not very nice, kind of close to the event horizon, things get a little bit complicated numerically. So we use the null constraint as a tracker of these kind of areas. And so when we deviate away from the null constraint, so if H is kind of within a certain tolerance of 0, we decrease the step sizing, so then you can take smaller steps and be a little bit more careful around places like turning points and where it gets a little bit hard to integrate. And then when we're in kind of a well-behaved area, we increase that step size and back up. And then, yeah, like I said, we track position and momentum, and I'll be showing some plots of that, which I've actually found people finding really interesting. And it's just a different way of kind of looking at the same results that everybody knows. So yeah, very quickly, just to go over kind of this image plane sampling so you guys can have it in the back of your head. We test different beta values and also different alpha values. And when by kind of changing these initial momenta, we're going to be able to sample different parts of the image plane. Okay, so one of the really fundamental aspects of our code is using kind of being able to classify these trajectories and finding the critical impact parameter that's going to contribute to the black hole shadow, and also the ones that contribute to the photon ray. So we use the bisection method. It's really easy to understand and easy to implement, and it also is robust. So basically we decide, we kind of classify, we shoot a lot of trajectories. We classify whether they escaped or whether they plunged. And then we take the last one that plunges and the first one that escapes, and that becomes a new bracket. And then we iteratively decrease that, cut it in half, and kind of reclassify. And we get closer and closer to this critical impact parameter. And you can set this tolerance to however many digits you want. We did 10 to the -6, but you can easily make that, even more close, I guess. So yeah, you can kind of see it on the image plane as well, if that is kind of how you want to think about it. So yeah, you just shoot a bunch of trajectories, and then you kind of classify and get closer and closer to that critical point. We also were able to do it on the other side. So here we're kind of shooting a bunch of these values and picking, and then we're also able to do it on the beta axis as well. So if we're looking for a specific initial polar momentum, we can find that using the same approach. So this is really nice to have kind of both of these when we're trying to fill out the critical curve and make it nice and smooth. It's nice to have kind of that flexibility. Yes.
I guess it's monotonic, but what if it's not just monotonic in a way, like you would have like the bisection method meets that?
Yes, so it does. That is kind of one of the limitations of the bisection method. You need that very clear transition, or like a root, for example. So yeah, that is something that you really just have to track, I guess. So like something for me, I have been testing different metrics, and yeah, it has not been completely monotonic. I just kind of print out the classifications and then kind of zoom in on that area. So yeah, it does require a little bit of maybe manual, investigation, but for a nice curve, for most of what we have looked at, it has been a monotonic plunge escape or escape. Okay, so now we're going to go into some validation results. So we started with Schwarzschild and curve, just to really make sure that our code is working for the easy cases, I guess. So you can see critical curves. You can see in blue the ones that our framework reproduced, and then Schwarzschild in gray, and then the analytical critical curve in red. So the blue and the red are overlapping very nicely, which is awesome. You can see the shadow deformation and kind of translation as we increase spin. So again, we've all seen these pictures before, but this was kind of our first result that shows that we're doing something right.
So what's these curves agree with precision? So the numerical curve?
Yeah, we haven't really calculated that, the error in which kind of they don't overlap, but, that is something that we could probably use. Yeah. So then we get into some radial evolution and, azimuthal evolution and polar evolution. So this is something that it makes intuitive sense when you're thinking about curve, but maybe you haven't seen this type of plot before, especially in the azimuthal direction before. So we zoom in, we look at, we classified a bunch of trajectories as near critical, and we kind of look at how the radial coordinate evolves with time. This is coordinate time. And we zoomed in on kind of the interesting part of the photon region. So you can see that this is a kind of moderate spin, so there should be some kind of separation, some frame dragging presence. So you can see the separation of prograde and retrograde radii. Again, pretty self-explanatory. The coordinates or the photon kind of linger near this photon region for a long period of time. And then we've looked at, I'm just showing one spin, but we've looked at kind of a short shield, a moderate, and then a very near extreme case. You can also see, which I'm not sure if I can zoom in. No, I can't. You can see the azimuthal coordinate as a function of time. So this is the total accumulated azimuthal coordinate. You can see there is some frame dragging starting to become present. So one's at maybe -20, one's a little bit above 20 for prograde versus retrograde. And then you can see this sort of oscillation, which I will get into in the next slide. But this is something that we've kind of tried to explain and looked into a little bit more that maybe you don't get in other plots. So yeah, we basically see some frame dragging effects and some asymmetry. And then we have our polar coordinate, which oscillates from the North Pole to the South Pole. So like I said, I'm going to talk a little bit about this azimuthal effect in curve. So we just zoomed in on one example trajectory, near critical trajectory. And you can see that the oscillation of phi dot is really lining up nicely with theta. So our theory is that as the photon is kind of bouncing between the North and the South Pole, the azimuthal speed is kind of changing. So it's not a constant velocity, which is kind of interesting, which I don't know if people have really looked into this too much. But yeah, so it's basically just kind of like speeding it and slowing down.
So what's, for this particular trajectory, what's the angular momentum of the photon, or the specific angular momentum? So angular momentum by the end, because you normalize to one.
Yeah, so this is just an example where our p thetas, our initial polar momentum is maybe 3, but we're expecting that this oscillation happens with all of the critical trajectories.
I understand that you keep one conserved killing constant of motion, right? Regard connected with the angular momentum. So what's the value of this parameter in this case?
I'm not entirely sure, to be honest. I mean, the only conserved quantities that we have is energy and one other thing, I forget. But
Carter constant.
we do not have the Carter constant. Yes.
Yeah, I'm asking because I think some of this behavior you can probe them analytically, especially close to these spherical photons. And what essentially determines the motion and its behavior is the angular momentum. That's my question.
Yeah, so I think what we're kind of seeing is that this is going to be happening for all the different initial languages.
But the angle you're talking about is the smooth one, right?
Yes, exactly.
Right, but then it depends on how you shoot it also. Because then you could have something which is purely equatorial.
Yes,
so like element,
but this is approaching one of these.
I understand, so, but that is another initial division. Because you could have just something with angular momentum, whatever, and the equatorial, and then you wouldn't have the full motion. That's why I was, so Yiddish is for curve.
Yes, this is for her, yes.
But for curve, each orbit has still the served constant. You agree?
Yes,
Yeah.
but we
Right.
didn't
And this
assume.
is exactly what is determining this sort of, initial theta motion, right?
Yes,
In
yes,
fact, will be zero for equatorial motions where you still have an angular momentum.
So in current, there will be a direct mappings, because these orbits are very specific. There will be a direct mapping between this p theta and this phi.
But you're talking really about the photon orbits, right?
Yes,
Yes.
they are intrinsically connected with the critical.
Which are connected to this,
Yes.
but in general, and that I understand. So for the photon orbits, right? So the spherical photon orbits, then there's a constraint
Yes.
in the
Yes.
J and Q.
Yes.
But in general, that's not the case.
Yes.
So I can send something on the equatorial plane, Q equal to 0, and J equal from 0.
Yes, yes.
And that could also approach the light ring. But then it would have a theta motion.
Yes.
Right. Anyway, sorry to disturb you.
Okay, that's
But
okay.
then it will head to this little discussion between
Yes.
them.
But yeah, these are,
Considered here. Yes.
this is definitely a non-equatorial,
That's obviously not.
yes. Okay,
Yeah.
oh, sorry.
No.
Okay, so just to kind of quickly go through some more results, we were able to calculate the Lee time, which you can see the nice equation up there for it. So basically, this is the instability of the photon region, a nice quantitative explanation of how the photon region is kind of acting. So we were able to plot the, basically the Lyapunov time describes the instability of how a photon is approaching or really leaving the photon region. So if we're able to plot that, we can linearize it by taking the log, and we can calculate the slope. And we're calling it TL, people call it lambda. And this is really important in not only kind of quantifying the instability of the region, but also in gravitational waves, you can connect it to the quasi-normal modes. So yeah, this is just kind of an example abstraction of how we do it, but we do it for very many different trajectories, and then we've seen a very nice result with at least Schwarzschild, and been able to calculate what that is, because that's just a known quantity. So we can see for the Lyapunov time across spin, we tested 3 different spins. You can see the asymmetry kind of start to grow. The Schwarzschild should be the exact same. It's 5.196. And you can see this kind of asymmetry getting larger and larger as you increase the spin. For the prograde, this is showing that in the near extreme case that the prograde is spending more time near the photon region, which makes sense because you're pulled closer due to frame dragging. And yeah, this is just kind of a measure of the instability of this region. And a nice kind of quantitative explanation of what's going on rather than more of a qualitative.
Sorry,
Yes.
for one given spin, does correspond to different trajectories?
Yeah, so we took,
or-
yeah, so you can see the individual ones. So there is some variation, which I think will get better if we test more values, but really this was just a validation test. So in something like one of the new metrics that we're curious about, we'd probably test significantly more trajectories. But yeah, so each of those individual dots is a different trajectory, and then we just took the average.
But sorry. Then this Lyapunov time is a quantity that is depending on the angle, because I imagine that if I have an image, if I shoot a photon on one side, that would be prograde, but if I shoot it to the other side, it would be retrograde. So
Yeah,
it's
so-
something that should vary along the contour of the.
Yes, so we look at, these are all going to be near critical trajectories, and then, yeah, we look at the prograde version and then the retrograde version. So that's why we have two different lines here. And you can see that asymmetry between prograde and retrograde as the spin increases.
And when you say the mean, it means that you're shooting close to the critical trajectory, but for different, theta angles, like initially.
So- No, so we actually calculate this for one specific near critical trajectory.
But not equatorial?
And then, no, not
It
equatorial.
doesn't need to be equatorial, right?
So yeah, we kind of, we vary our initial polar momentum and kind of calculate that we have enough time, and then we take an average.
I see.
For
So
one
then it's the initial polar momentum that you are varying for
Yes.
the average. That's
Yes.
my question.
Yes.
But why individual level of time differ from each other?
Sorry?
Why individual values of level of time,
Yeah,
why they differ from each other?
Yeah, that's just error.
It's like numerical.
Yeah, they should all be the same. This again, is going to be fixed by just testing a lot more. We only had, so much time. So there is some variation, but it's not too bad. And we did check it for Schwarzschild, and it agrees to maybe 10 to the -3, 10 to the -4, something like that. Okay. So we also calculate delay time, which is the time between successive higher order images. So we are able to plot our theta, our polar trajectory or coordinate, and then measure the, we look at a half polar oscillation and measure the time between that. So you can see the time kind of between these higher order images. Again, this is very important for photon ring, kind of direct release. And then again, you can see how delay time changes with spin. We see that it's agreeing very nicely for prograde, retrograde, Schwarzschild, which is expected. And then you can start to see this asymmetry starting to grow. And again, more time is being spent in the prograde side for the higher spin. And then the last one that we are able to calculate is the azimuthal phase shift. And this is really just within that delay time, how much our accumulated phi is changing. And again, you can see this nice asymmetry start to grow. What I think is interesting is the retrograde is pretty consistent throughout the increase of spin, but I think that it just is kind of staying far away from this photon region due to frame dragging. And then you can see it start to increase for prograde, which again makes intuitive sense because we know that the extreme case is going to be pulled into this photon region further and spin around the platform. Yeah, so we were able to find this. This is also really important for finding periodic orbits. So I didn't put it in this presentation, but this is something that we look at. But this is like close to a integer of pi. We found a periodic orbit. So that's something you can look at as well. Any questions on Kerr?
Sorry, maybe.
Yes.
So here, do we expect some spread of the points for one spin, or because you said for the enough time it should be all the same, right? But
Yes, these should, so it should be the same for a specific spin, right? Yes, these should be all,
Okay, so
like, if it was perfect, yes, it would be one number for each spin, for a prograde and a retrograde. Okay, so some preliminary results, we were able to I just wanted to show that the framework works for a non-separable metric. These are all very nice for Kerr, but that's not the point of our project. So we look at a quasi-Kerr metric. Again, this is our very preliminary. So yeah, we're kind of still testing with this. I don't want to make too many conclusions, but we looked at the Glandadakis and the Bach metric. This is a very nice kind of perturbation from Kerr, and it has this nice control deviation parameter, so we can kind of test how far away from Kerr we are and kind of see as we go further away from Kerr, what changes, what stays the same, these types of things. It also has a different quadrupole moment than Kerr, so this is Johansson and just use this metric to test no hair errors and things like that. And yes, so this has been extensively studied by Johansson, so this is a really nice kind of first natural step into a new metric or a non-separable metric that we have some results to kind of compare against. And we're still kind of working on this comparison. But yeah, it's a nice natural kind of first step for us. So here's the metric. You can see it is a deviation from Kerr. Epsilon is our deviation parameter, so we can vary that and get, further away from Kerr, closer to Kerr, whatever we're curious about. And then you have, the metric defined with each. These F1 of R and F2 of R have a, it basically takes the form of ln something over 1 minus 2 MR, something like that. So basically, it's defined for radius equal to 2m. That's just something to kind of take note of. And this is something that we have to really take into consideration, this radial cutoff, which I'll explain in the next slide. But yeah. So we set up the parameters the exact same as Johansson, so we could really easily compare our results. And this metric really works for very, very small, or I guess just non-extremal spins. So we did spin equals 0.4. And a little bit of a non-equatorial or edge on observer information table. Okay, so like I said, the radial cutoff is very important. We can't get, too close to this 2m value. Johansson has a very nice explanation of how the radial cutoff needs to be kind of investigated with different levels of spin. So we started with a, I guess, for epsilon equals 0.5, which is what we're curious about, and spin equals 0.4. We chose 2.6 as our kind of first radial cutoff, but since then we're working on kind of making a function based off of what the spin is, what the epsilon parameter is, and then what our radial cutoff should be, so we can get a little bit closer. But 2.6 should be fine. These are basically explaining where the radial cutoff has to be in order to have kind of a physical, a meaningful result. So you can get non-Lorentzian below the dark line. So we're somewhere kind of in that.
This is outside the horizon.
Yes. Yeah.
So
So we don't know what the horizon is.
okay.
Right. So
So can you, I don't know if you already said, but what do you mean by physical regions?
yeah. So it's non-Lorentzian underneath this dark line, and then the dotted line is maybe like somewhere in the middle, or like a just kind of fishy area. So we want to stay somewhere above that that dotted line, and this is going to change for whatever epsilon parameter and spin that we're curious about. So yeah, what we're working on now, which I don't know, we just started this like a couple weeks ago, so we've made a function though that kind of solves for what this radial cutoff has to be based off of your parameters that you set. So that
Are there some set of parameters such that these problematic regions are hidden within the horizon? So you can trust the space-time until the horizon, then any potential issues are kind of hidden away inside.
yeah, but we don't know what the horizon is, so we're kind of treating this as in our head like a horizon, right? So we don't want to be approaching this cutoff. We get as close to this cutoff as possible. but we don't have a horizon solved for this.
In this particular case, I understand that this quasi-curve parameterization, it depends on the set of parameters, if I remember.
Yes,
So for a certain set of choices of parameters, you can perhaps have these problematic regions hidden away, so it's...
Yeah, so that's kind of what our function does. We solve for this kind of cutoff as close as we can get to this problematic region without crossing it, right? So, you know,
You
may not. You may not. Yes, perturbation may make GR out not equal to 0.
Okay. But if you don't have an horizon, you eventually always have this problem. The advantage of, well, but in some cases you may have an horizon.
Yeah, but my issue is, can you define an horizon in a generic way?
Well, in a space-time that is asymptotically decided, kind of.
Yeah, but can you find a solution? Can you always find a solution for an horizon?
No, that's not the
I
point.
mean, it's leaping. You can investigate the phase horizon even from there.
My point is, if you can make a tuning, if you can tune the set of parameters such as you can have a space-time that where you can trust everywhere until an horizon exists.
Yeah, my issue with that reasoning is that you have about an horizon first.
Yeah, sure. But if you don't have an horizon, well, having an horizon is kind of not the best case scenario where you can hide away this knowledge.
Which is what you are considering.
Yes. So if the space-time would be horizonless, then you have nowhere to hide.
yeah, so basically the whole idea is that this is, you know, once you get past a certain radius, it doesn't look very physical anymore, you can't really trust what's going on. So we've developed a function that kind of adapts this radial cutoff for whatever spin and whatever epsilon requires. So yeah, just keep that in mind when you see the results, because again, this is it's not perfect yet. Just to give a little bit of a kind of physical intuition about the epsilon parameter, this is going to be changing the flexible moment, so it's going to be changing the critical curve from more oblate or prolate. So yeah, it just is kind of switching things in different ways. So this is what Johansson's critical curves look like, and he did epsilon equals 0.5, negative 0.5, and then which is epsilon equals 0. So again, we did the same thing. Where, you know, again, this is very preliminary. We're not super confident on our positive 0.5. There's a couple fishy areas which I didn't want to show. But this one looks really nice. It is flipped. That is something that we're looking at, but it might just be a different definition of our axes. But yeah, so we were able to plot epsilon equal to 0, what the current analytic, so these should, you know, line up very nicely, which they do. And then we can see our epsilon equal to negative 0.5. So this seems to be working really nicely. Something that we are going to do is, apparently there's this website where you can actually find out what those values are on like an image. So we're gonna test that. So yeah, qualitatively it looks pretty nice. And so we're able to maybe start looking at new results, but you know, I don't want to make any major conclusions yet until we test that. So again, this is just kind of a physical intuition of how these photons are working, how they're kind of approaching this kind of weird, or maybe a horizon area. Again, this is just physical intuition. Okay, so now we look at the radial evolution of these near critical trajectories. And we see some maybe weird stuff. Again, we have, once we really are positive about our critical curves matching with Johansson, then we can start making some real kind of physical claims. But you can see this almost oscillation or bouncing between two regions of the photon legend. So kind of interesting, but we don't want to say anything too declarative here. So we actually kind of just zoomed in on the near critical trajectories that behave nicely in this radial evolution plot. So, most of the retrograde ones stay, and we kind of just threw away the oscillating ones just for now, until we're super, super sure about our radial cutoff and that the critical curves are nice. So for the rest of this kind of results section, we'll just be looking at a specific set of critical trajectories that are behaving nicely. So again, we see kind of an asymmetry start to form between a retrograde and prograde orbit. And then you can see that this is behaving a little bit like her, where these trajectories are spending a lot of time lingering near the photon region.
Sorry, I cannot read the label on the y.
Yeah, sorry, I can zoom in. It's R of T, but I know, I just didn't want to put more slides. It's already long. Yeah, I can actually just keep it like this. if you want. So now we can see our azimuthal coordinate changing as a function of time. Again, you start to see this asymmetry between prograde and retrograde. These are a lot nicer oscillatory-wise, which again, we're still looking into, but it might just be the fact that it's hidden a little bit more. It might just be a smaller amount, so then it kind of gets overshadowed by the rest of the plot. So again, something that we're looking into, but a pretty easy thing to look into because we have all of these coordinates tracked. And then just the polar evolution looks really nice. Again, it's just an oscillatory behavior. And we did just zoom in on the retrograde values because the prograde values are a little bit crazy. And you can't really tell much. So we can see this nice oscillatory behavior. You can see, there's not that much difference between the different epsilon values. So that might be something interesting. The prograde values, though, if I remember correctly, they almost, they're periodic, but they don't hit the same exact point everywhere. So the same minima. The amplitude actually changes as we go through time for one critical trajectory. So that's something weird that I haven't seen before. So.
Can I ask you, so these epsilon values that you're taking, how do they change the global properties of space-time compared to?
So it changes, it's a perturbative deviation from curve.
Right, but quantitatively, how much does it change percentage-wise, say, the mass of the angular momentum of the epsilon equals to zero curve level that you're kind of
That I do not know.
Because if it's, that would be interesting to see.
Yeah.
How much you're departing in terms of global quantities from curve,
Definitely. But this is just, again, just very preliminary results that we. But yes, definitely. To kind of get a better sense of what this deviation parameter is doing. But it does definitely change the quadrupole moment, which is something that we're looking into a little bit more. So for the up and up time, we're able to extract it for specific, again, trajectories. But we're coming into a little bit of a question mark with some trajectories. So we expect this nice exponential decay as we approach the photon region. And then you can linearize it very, very easily. However, that's assuming that it's an exponential, right? There's nothing that says it has to be an exponential for an arbitrary metric. So again, something that we're looking into, and it just might be the fact that an exponential is not the correct relationship. So this is something that we're looking at. Obviously, the one on the right is not fitting very nicely. It's fine, but and again, this could just be something where we need to test more. We need to kind of look at different types of trajectories and really zoom in on this area. So something that we're looking into and something that could be really interesting, especially, I personally have only seen exponential decay in the Lyapunov time, but it could be really cool if it's not. So again, preliminary results, but we tested a couple critical trajectories. We're starting to see, I don't want to make any, declarative statements here, but we're starting to see at least a trend with epsilon parameter, deviation parameter in the time. So we're starting to see some kind of change happening for both prograde and retrograde. I can actually do that. So now we see the delay time we looked at. On the left, we have a nice, easy value that we were able to calculate. And then on the right, we have one that we're really starting to think a little bit more about. So the delay time really is determined by matching extrema, right? So it has to have a matching minima and a matching maxima. If they don't have that, then there's really no delay time, right? That's the definition of delay time. So it could just be that that specific trajectory doesn't have one, a higher order image, but again, something that we're looking into. Some of the critical trajectories do have nice.
Sorry, can you repeat the last thing?
Yeah, so the delay time is it's defined as a photon that, subsequent photons that reach the same point, right? In the half polar orbit. If they don't, this plot on the right has no kind of matching extrema, so, maybe they're just, there's no higher order image, So again, something that we need to think about a little bit more. This is just one example. We can see prograde, we didn't have any, we only had a couple values. But again, for delay time, you can see some kind of trend starting to appear for at least retrograde. Lastly, we have the azimuthal shift, again, which we were able to calculate. This is actually a periodic example, which actually kind of worked out nicely. But again, if you don't have a nice matching extrema or delay time, then you really can't calculate the phi shift. So again, something that we need to think about a little bit more. But for most of these, or for some of these did work. And again, you see some kind of trend starting to appear. This is actually staying relatively consistent, which is what we saw for Kerr as well, for retrograde. Okay, so just to wrap up, we were able to develop and validate this generalized ray tracing framework. We were able to kind of take the Carter constant out, avoid separability, and validate it for Kerr, and then kind of take this next step into a non-separable metric that has kind of some physical parameters that we're curious about. We were able to not only get the critical curve, which is a more qualitative observable, but we were also able to calculate these critical exponents that give you a quantitative explanation or description of what's going on in the photon region. So looking ahead, we're working on the lensing exponent, which is kind of the last exponent that we're curious about. We think we know how to do it, but we haven't done it yet. So that would be kind of the last critical exponent in this set that we're curious about. So we should be able to characterize the black hole even further. We also, obviously, the next step is to kind of extend it to more metrics. That's the whole point of this. So quasi-Kerr, we're curious about because it has more of like a physical kind of meaning, but we're curious about other metrics. I've worked a little bit with Johansson, which is separable, but I'm kind of working on how to make it non-separable and then see how it changes. So yeah, open to other metrics that you guys are curious about. And then kind of just working on making these images a little bit more, taking into account maybe plasma or radiative transfer to kind of get an idea of a more physical, more realistic kind of photon trajectory. And that's basically it. Yeah, and gravitational waves and stuff.
thanks a lot for the talk and for the nice keeping of time. So we have time for a few questions. Well, I can start. Like,
Well, if there are no other questions, I can do a very small one. So I noticed that when you explained the numerical method, you mentioned that the code is currently using the Runge-Kutta for method.
Yes.
But well, I was thinking that for things that are could be a bit delicate, like calculating the Gaussian exponents that you need well to deviate very slightly from the critical curve. It would be good to take advantage of the fact that you already are solving Hamilton equations to use instead of a symplectic integrator. So is this something that you are considering or?
No, so personally, I'm more familiar with, like a Runge-Kutta. That's just what I've kind of been taught. But someone also, when I presented this at Harvard, they said, they mentioned the leapfrog integration. So there are definitely other types of integration methods. This one, I mean, when I'm coding, I always tend to kind of go for something that I know really well and is, easy and, easy to implement and easy to understand. So that's kind of what I chose.
Well, the leapfrog scheme can be easy, maybe easier to implement than Runge-Kutta because it only has 2 steps instead of 4 steps, no? And the only thing is that they are staggered in time.
Yeah.
But it has the advantage that indeed it preserves all the things that are supposed to be preserved.
Yeah, I haven't really looked into it that much, just because that was like last week, to be honest. So, but yeah, I mean, I'm open to other methods, other integration methods that could make the code faster or more robust, for sure. But I definitely think that the biggest thing about this project is to make sure that my favorite part about it is being able to really just change one cell and have, as long as that stays the same and I get still the same results, I'm open,
So, go ahead. So you mentioned you had in the beginning some adaptive steps that were kind of connected with the question. So how did you implement it in practice? Because there are different ways where you can implement this.
Yeah, so I use the null constraint, so the Hamiltonian should be 0 everywhere, right? If it deviates away from 0 a specific amount.
So say epsilon, not what, but how do you adjust this?
Yeah, I decrease it by 10%.
Okay.
And until I continue to track h, and once it kind of gets back down to 0, then within epsilon, then I increase the step.
But I mean, I had also a question about the code in general. So, is there a plan to make it public? I mean, I understand that now it's very preliminary, so you need more testing and getting the reward out of it. But
so
the long run.
I will say there are. This is not the first generalizable ray tracer, right? There's other ones, and they're probably quicker than mine. But what makes mine very kind of unique is kind of all the calculations that it does and all of the tracking that it does. And I made this specific for, a problem. So yeah, I mean, once I kind of clean it up and, have some more validation results with, an actual new metric, not just her, then I'll put it on GitHub. Something like that.
So the curiosity in what language?
Python. Yeah.
Oh, I can ask maybe, one question and one suggestion, since you said your code is in Python. Well, there's other codes, as you said, probably you know about Python. I don't know if you know about it, but it's a code. It was actually done by someone that was in the group at some point.
Okay.
And then moved to work in ESA, European Space Agency, and they had there, and then it was made public. And so it can also deal with this type of space times.
Yeah.
It's publicly available. And some other people have run it here in the group, and so maybe you'd be interested in taking a look and see how it compares and what it does.
Definitely.
I hope, then you can find documentation online.
No, definitely. I think, when I kind of discovered that there are other ray tracers out there, and again, probably faster than mine, it was a little discouraging. But I do think there's value in kind of developing it yourself and also whatever, like,
And they are in control of everything. that goes into it.
and also
Yeah.
what, quantities, I don't know anyone that is doing critical quantities for, a quasi-curve.
And if you want to change something, then you know how to do it.
Definitely.
The suggestion was, well, it's kind of, a long-term or medium-term thought, but many, you've gone into this parameterized variation string curve, that's nice, that's the way of doing it. But a lot of non-curve metrics that are actually solutions to some field theory model, they are numerical rather than analytical.
Yeah.
So, then this is another step that you might think about in the future, is that how you import a numerical metric and then you run your code on top of it rather than just some functions.
Yeah.
That's something that would be valuable in the sense that it opens up, the target metrics that you can deal with.
Yeah,
and tackle with your
definitely.
code.
Yeah, I think, next steps is really kind of, getting the quasi-curve nice, get some new results for that, but then, really just open it up to another metric, whatever we're curious about.
Coming back to the level of exponent, that's numerical calculation of it. So when you calculate it, which order of images do you use? Because all these exponential formulas and so on, they're like asymptotic formulas. So if you use, probably you will have some additional error if you consider lower order images.
Yeah, we really didn't really take higher order, different values of n into consideration with the up and up exponent. We really just look at whatever near critical trajectory we have. The delay time and the phase shift is where we kind of get it more into the higher order images.
Okay, well, so I think we can stop here for questions, and of course you can ask more during lunch and this afternoon. So thanks again, Kara.